I'm Jonathan Ochshorn. This is part 4 of a series of lectures dealing with health, safety, and welfare in buildings, and in particular, how those aspects of architectural utility or functionality can be constrained by politics and economics and damaged by expression. Part 4 deals with the politics and expression of structure. So we start with loads. We're now dealing with structure. There's some loads which are very unpredictable. Things like hurricane, earthquake, even live loads, people jumping up and down in a building. And the fact that they're unpredictable is important. That is, they exist in a probabilistic environment. We can represent it as a kind of a bell curve with the vertical axis measuring the probability that a particular structure will experience a particular load magnitude over the course of its life. The x-axis, the horizontal axis, showing the load magnitudes corresponding to their probability of occurrence. So it's like this classic bell curve. The concrete column represents the building structure. The blue arrow on the column schematically shows how the load gets bigger or smaller depending on which assumptions we choose. But none of this yet indicates how we design the concrete column, how safe it should be, and how politics and economics enter into our calculations. To understand the politics and economics of structural safety, we need to consider not only the loads, but also the strength or resistance of the column, shown here as a green arrow resisting the loads. This corresponds to the green line on the graph, which is placed to the right of the expected loads. In other words, placed so that the magnitude of the resistance or the strength is greater than the magnitude of the load. If the magnitude of the resistance or strength becomes smaller than the load applied to the column, well, then the column fails. There are cost implications directly corresponding to the position of that green resistance line. As it moves to the right, the structure gets stronger and more expensive. As it moves to the left, the cost of the structure decreases. But this resistance also exists in a probabilistic environment in which the actual structural strength may be less than or greater than what was expected. What causes these uncertainties in structural strength, that green line? Why isn't it just able to be computed and built and we know exactly what we're going to get? Well, there's 3 issues that could affect the ultimate strength that you get. And those issues are design, manufacture, and construction. We'll look at each of them in turn. By the way, this is a finite element model of Milstein Hall. That's the bridge and the stair under the dome. And this is the structural model. Even though the design, like in the case of Milstein Hall, is based on sophisticated modeling using structural analysis software, any model is only as good as the assumptions made by the designers and of the structure and of the software. So take the case of this Millennium Tower. This is in San Francisco. I took this video when I went there last month, and I came back with COVID, but I'm not blaming the Millennium Tower for that. See what they're doing? They're drilling piles, and the building's already occupied. It's been occupied for more than 10 years. They used piles that were so-called friction piles that didn't go down to bedrock. Why not? Because it costs more money to drill the piles down to bedrock. It was a particularly long way from the surface. And there were other buildings in San Francisco that had used friction piles successfully. So even though it's not quite as good as piles that go down to bedrock, they're going to try it because it saves them a ton of money. And then what happens is the building starts sinking. And not only that, it starts tilting. And there's people living there. And this is a luxury development. And so they have a lot of money to hire lawyers and complain. So ultimately, almost 15 years later, they found a resolution. And at a cost of over $100 million, they're now drilling 50 new piles, which you see them doing all the way down to bedrock, and are somehow going to anchor the existing foundations into these new piles and thereby stop the tilting and the sinking. The point is, in the design of buildings, you have a certain probability of being wrong. This is always the case. Here's the second one is manufacturing. And I'm giving you 2 examples. In the manufacturing, in one case of concrete, in the other case of steel. In both cases, the interest of the manufacturer, or in the tester, in this case, in the case of concrete, of increasing their profitability led them to cut corners and fabricate data. So in the case of the New York City concrete scandal, a lot of really famous buildings were built using concrete where the test to make sure that the concrete was strong enough was fabricated, including the World Trade Center rebuild, the so-called Freedom Tower. The good news is that they went back, they took little cores of the concrete and they tested them, and they found that the concrete was okay. So it wasn't that the testers were trying to sell defective concrete. No, they were just trying to save money by not doing the tests. So the concrete turned out to be okay, but it's still a bit of a scary thought. You're deliberately testing the concrete because it's site cast and you really don't know what you're getting unless you test it. And you're relying on the testers to say, yeah, this is okay. And if the testers are fabricating the data, well, that's a bit of a scary thought. But it's one of the reasons that manufacturing may affect the strength of the structure. And the same thing happened with Kobe Steel in Japan. They were fabricating data about the strength of the structural steel. The third one is construction. So even after design, after the manufacture, now you're actually putting the building together. And we were talking about the Milstein roof and why it still leaks. And I was speculating about how its construction could have led to certain problems with the leakage of the roof, as well as the design, the fact that it was not sloping enough. So this is the case of Champlain Towers, and we don't have to go through the details, but there's some evidence that it was not constructed properly. Some of the steel rebars were not placed where they were supposed to have been placed. There also may have been design errors in this building as well. So it can be more than one problem, but construction can cause problems if contractors are taking shortcuts, especially not putting steel where it's supposed to be. This is implicated in a lot of the earthquake damage, for example, in Turkey, but also elsewhere. In the case of Champlain, some of the deck had little or no reinforcing steel, too much steel in some other places, causing overcrowding. They may have placed reinforcing steel improperly in some of the columns. And economics is playing a role in all of this, including the fact that there's inadequate supervision, because all of these things cost money and nobody wants to spend the money. Here's an example, an article in the Times indicating that the owners, in this case, the owners are the tenants, because it's like a condo. So the tenants own the building, and they didn't want to pay for maintenance and upkeep of the building, because, you know, they would be getting a bill for like $80,000 to $200,000 each to do what was right. So even though they're living in the building and it's about to collapse, they didn't know that. On the other hand, they just didn't want to spend the money through their homeowners association. We don't have to look at them in this case as the residents of the building. We can just look at them as owners who are subject to these same constraints of having to spend money and not wanting to do it. And then in the political arena, in the legislature in Florida, after this disaster, they were unable to agree on a bill that would mandate inspections and having co-ops have a minimum maintenance reserve fund to protect against these kind of disasters in the future. Finally, after a year of wrangling, they came up with a compromise. And again, that's that balancing, right? It's not the greatest piece of legislation. It's not the worst. It's just this balance. So, you know, they don't have to do inspections except after 25 or 30 years, which is a long time. Probably a safer attitude would have required inspections earlier and more often. But again, it's this balancing of safety against cost. So notice that the probability of structural failure is represented by the area shown in red where the two curves overlap. That is, where loads on the structure exceed the structure's strength. That's that red area. So if you want to reduce the probability of failure, the cost of the structure increases. What we are really doing when we shrink the red area where the curves overlap is increasing safety factors applied to the structural strength. These safety factors, however, can never absolutely preclude failure, since there will always be some red area in the curve. And I should add that the steps taken by the Florida legislature to mandate structural inspections certainly make buildings safer and reduce the red area in the graph, not by changing the safety factors, but by directly narrowing the probabilistic risk curve shown in green. In other words, with greater oversight and inspections, the structural strength will be less likely to deviate from its assumed value. Such mandates also increase the cost of the building. The determination of where exactly that green line should be placed, therefore pits the added cost that comes about by requiring additional structural strength and mandated inspections against the added benefits to society. Just like in fire safety, the benefits include less property loss, less loss of human life and injury. These benefits increase as the red area increases and the cost of the structure gets larger, or decreases, that is. So you see, it's complicated, but it all comes down to this balancing act of cost and benefits. And you can never absolutely preclude failure. There'll always be a tiny little red area, but what you want to do is make that area as small as possible. And the only way to do that is to bring the green line further to the right. And when you do that, you're making the structure stronger, or you're increasing the inspections or maintenance, and all of that increases the money. And so it's, again, you're pitting someone's profitability against someone else's safety. That's the context in which you are working as architects. It becomes a political decision then, this acceptable risk of failure, not a scientific decision, a political decision. Industry groups corresponding to the major structural materials, they each have their consensus-based standards. I'm picturing the steel, the concrete, and the timber manuals, which are referenced in the International Building Code, which is the model code, but then it becomes legal because the codes are then adopted by each individual state legislature. And in this way, the political and economic content of structural safety is ensured, even if the actual cost-benefit calculations are rarely made explicit. What about structural expression, you're thinking? This was all about the politics. What about the expression? Well, I've identified, let's say, 3 potential problems with structural expression that can compromise health, safety, or welfare. And the first potential problem is that, at least in a certain class of extravagant structures, those with deviant and unconventional structural geometries, far more material must be used. And this creates potential problems with what you might call opportunity cost, which is the stuff that you can't do because you're doing something else. And also, it makes it less sustainable, because in using more materials, you are burning more fossil fuels and so forth. Here's another little animation GIF or GIF that I made using real structural calculations. I made this little model of a simple structural frame and figured out what kind of steel would be needed to make it work according to these loads that I've placed, 500 kips, 50 kips lateral. So it's just a simple structural frame. And what you can see is that as you make the frame more deviant, like angled up to 20 degrees, it basically doubles the necessary material cost and weight. Obviously, this is not going to be the same numbers for every particular structure, but it just gives you an idea that making these deviant structural moves is not cost-free. The unit weight of 2-story Milstein Hall is more than double that of the 100-story Hancock building in Chicago, designed by Skidmore, Owens, and Merrill, and their legendary structural engineer, Fazlur Khan. And he had the idea, let's make this building as efficient as possible by putting the truss work to stabilize it against lateral loads on the outside. And I won't get into the structure of why that makes sense, but it was a very radical move, because at the time, this was a very controversial thing to do. What? Put diagonals on the front of the building going through people's windows? Is that possible? You know, it was a form of defamiliarization from the early 1970s. Nowadays, it looks pretty tame, but back in the day, it was a radical move. But it was a radical move that, rather than increasing the cost, as in Milstein Hall, actually made this one of the most efficient tall buildings ever built, because it was a form of defamiliarization that was based on the rational calculation of structural cost. The competition driving defamiliarized avant-garde architecture has gotten more extreme in the past several decades, aided but not caused by more powerful modeling, computational, and fabricating tools. Here's the second idea, which is maybe not quite as important, but it's the idea that, you know, some forms of expression want to create a sense of continuity and don't want to indicate that there actually is a need for isolation or separation joints. So this is a section in a plan of a typical column going to a foundation and intersecting a basement slab. And when you do that, you know that there's going to be a lot more load coming down on the column than sitting on the slab. And there's a lot different conditions supporting it. The slab is just basically resting on grade, whereas the steel column is resting on a more serious spread footing or possibly piles or caissons, whatever. The point is that they're going to have differential movement because they have completely different structural conditions. And if you don't want the slab to crack, you better put in some sort of isolation joint, which means you separate the slab with this kind of diamond shape or square isolation joint. It's really simple. This is a generic detail, and you see it in normal buildings all over the place. And then, we get to Milstein Hall, and either because they wanted this sense of continuity, or they just didn't know any better, they left out that isolation joint, and as a result, the slab cracks where it wants to crack. Right? It's going to crack. It just won't crack in a neat way. It'll crack in a kind of an arbitrary way. So that's the kind of moral of the story. Not that I'm picking on Milstein Hall. I'm also picking on the Johnson Museum, which leads us to the third problem with structural expression. And this is a big one, which has to do with thermal bridging. And it's mostly associated with this notion of a kind of a brutalist design. Now, I don't know, brutalism has not really been adequately defined. You can read Rainer Banham's book on the new brutalism, or I think there's a couple of new ones coming out. But the basic idea, and in the sense I'm using the term, is a kind of a misplaced notion of honesty. That is, you want to have a constructional and structural honesty where what you see on the outside is what you see on the inside. Like if you see brick on the outside, it's because it really is a solid brick wall. And when you go through the door, you'll see the same brick on the inside. Or in the case of the Johnson Museum, it really is just 1 foot of concrete. That's it. There's nothing else in there. I mean, it's reinforced, but what you see on the outside is the same concrete as what you see on the inside. This is a huge problem. You wouldn't be allowed to build this building today. But this was designed in the late 60s. It was built in early 1970s, right before the first of the OPEC-induced oil crises. It's the idea of expressing structure, and it can cause a lot of damage. Milstein Hall was also designed to express the exposed structural steel. And here's another great animation that I have made, which shows how the expression of the steel structure creates penetration, another thermal bridge, right through the insulated slab. And these are huge steel columns. There's a huge surface area. Steel, as you know, is a really wonderful conductor. It does a really good job of losing all of that heat or coolness, depending on the season. So it's a complete violation of any idea of continuity of the thermal control layer. And there's a lot of other thermal bridges in Milstein Hall that are not necessarily related to the structure, but this one is related to the structure.